Hi, kids. All right, so you should have done the little reflection smorgasbord. So, I just want to show you how you can draw where the image is going to be and how everything is going to happen. So, here is my Abraham Lincoln, the Vampire Killer. Although my Abraham Lincoln looks like he's waving a flag. By the way, okay, the movie Abraham Lincoln Vampire Killer, not so great, but the book, now that is good stuff. I when I read it, I figured that's probably history. So I would strongly recommend the book. Abraham Lincoln Vampire Killer. The movie, yeah, not so great. But anyway, so here's Abraham Lincoln. He is standing in front of a mirror. Okay, here's the mirror. Remember, the little lines represent the back of the mirror. Um, and he is going to see his reflection. If he's going to see his whole reflection, that means light from his feet have to go to the mirror and then go where? Well, if he's going to see it, oh yeah, to his eyes. So, does it make sense? I'm going to draw this light, but does it make sense that this could happen? And the answer is no, because that would violate the law of reflection. Light's not going to come in this way. Well, if that light came in this way, it'd bounce back this way. Okay? It's not going to bounce randomly up to his eye. So then, how do we do that? Oh boy, just threw my pencil. So, then, here's what I would recommend to figure that out. Well, if light is going to come from his feet to his eye, that light's not going to go up to here and there. Let's label some spots. So I'm going to label his eye level. Okay, so like there's his eye level. I'm going to label his top hat because the top of his hat, because we're going to need that later. There's where his top of his hat is. And then his feet are going to be down here. Well, guess what? If the light is going to go from here, hit the mirror to there, where is it going to have to hit? Well, it's going to be halfway in between there because it has to follow the law of reflection. So if we use our handy dandy, this is 1, 2, 3. I'm going to say it's just under 4, so it's going to be just under 2. It's going to hit someplace right about here. So this light would have to do this. It would go like this, and then it would go like this to his eye. Okay? Now, if I wanted to draw the normal line in, the normal line would go like this, because again, it has to be perpendicular to the surface. So it'd be something like this. Okay? And you can see this would be my angle of incidence, this would be my angle of reflection, and those two angles would be the same. They would be equal to each other. Now, Abraham Lincoln, the Vampire Killer, he has a brain. And his brain always thinks that light travels straight. Okay? I like to call this the Lineberger light law, or L cubed. Your brain always thinks light travels straight. And you might think, well, why does your brain think that? Because most of the time light does travel straight. Okay? And that's how we know where something is. So even though the light did this and this, your brain thinks that that light came from back here. So your brain is going to see an image of your foot back there. Okay? How is he going to see the top of his top hat? Well, the same thing is going to happen. It's going to go halfway between these two and looks like it's like 1.2 for me, 1.2 centimeters. So it's going to be about 0.6. So it looks like it's going to hit right about there. And so then the light would go from his top hat to there. And then from there to his eye. And again, if we wanted to draw in the normal line, perpendicular to the surface, it would look something like this. Okay, where this would be the angle of incidence, this would be the angle of reflection. And then, again, Abraham Lincoln has a brain, so his brain thinks that that light traveled in a straight line. His brain is going to think that that light came from back here. Okay, and he would see his top hat here, and in fact, his reflection would look something like this. I'm going to try to see if I can draw it. That would be his reflection, right like that. Okay. Now, a couple things. Because of this, and really because of geometry, this distance, okay, which is called SO, which stands for the object distance, is going to be equal to this distance, which is going to be called SI, which is the image distance. And just so you know, anytime we're doing object distance or image distance, it's always going to be object to the optical surface, or the optical object, in this case the mirror, and then it would be the image to the optical thing, in this case the mirror. Sometimes later on it'll be a lens, but it's always object to lens, object to mirror, in this case, image to there. In this case, SO equals SI for a plane mirror. So if you have a mirror that's flat, that is always going to be true. And then how much of the mirror do you need to actually see yourself? You only need from here to here. So that is the only part of the mirror that you actually need. So if you actually hung it correctly, if you were to move closer, that's as much mirror as you need. If you were to move farther away, that's as much mirror as you're going to need. That's it. Okay. This you'll also notice, see how these light rays back here, I drew dotted because they're not going behind the mirror. Okay. Your brain just thinks that they came from back there. It creates, this is what's called a virtual image, and we'll talk more about this later, but just so you are introduced to it. Okay. The reason it's called a virtual image is because the light rays don't actually go there. When you look in a mirror, can you see yourself clearly? Darn right. Okay. A virtual image doesn't mean you can't see it. It's just the light rays don't actually go there. Okay. The other thing I want to point out is in a plane mirror, the image gets reversed. You'll notice, hey, look, he's holding it there, and then he's holding it there. It got reversed. He's holding it in his left hand. He's holding it in his right hand. So let's talk about why it actually gets reversed. So let's say I have another plane mirror here, and here you are. This is a top view of you. You have this eye open, and you're winking this eye, and you're looking at the mirror. I know it's not a great picture, but you get the idea. So if I was to draw this, well, if they're going to, this is the only eye that's open, so light from their closed eye would go like this, and then here. Well, then their brain is going to think that that came from over there, and light from this eye would go here and straight back. Well, their brain thinks that it came here, so here is your reflection, and I don't know why I made you get bigger, but anyway, that should be the same size, and it should be the same distance away. But here's the thing that I want to show you. This person is winking the right eye. Okay? I'm going to turn it around. Ready? Oh, look. This person is winking their left eye. Do you see how that image got reversed? Okay? So, yes, in a plane mirror, the image gets reversed, which is why on the front of an ambulance it says emanskibla, because, if you were driving along and, it said ambulance on the front of an ambulance, and you looked in your rear mirror, it would actually say the Manskibla, and you'd be like, what is a Manskibla? I don't know what that is. I don't care about those flashing lights. I'm going to keep driving. Whereas if you look in your rear mirror and it says ambulance, you'd be like, oh, an ambulance. All right. Hopefully that helps. Bye, kids.